In Unit 2, we will talk about the universe, instructional methodologies to teach the universe in primary education. Basically, the contents that we will revise in this unit will be the universe, the Big Bang Theory, galaxies and stars, and the solar system. So also I want to say that in class we will work different strategies to teach the universe in the students of primary education. So let's start with the universe from the past to the present. In the next 10 minutes we will talk about the different theories and the evolutions of the theories that has explained the universe during the history. So the first thing I want to point out is what can be seen in the sky when we go outside at night, in a clear night, and we look up the sky. What can be seen? What is the origin of the stars? What is the origin of the universe? Everybody has ever wondered the origin of the universe, the origin of the stars. So there is a part of the science, astronomy, that is in charge to give explanation about the skies, about the elements, the objects that are in the sky. Astronomy nowadays is based on mathematics, physics, chemistry, and their goal is to explain the origin, the reason of the different objects, planets, stars, moons, galaxies that are in the universe. But in the past, astronomy was something very different. In the early history, astronomy was a mix of religions, mythological beliefs, cosmological and astrological beliefs. All these components were used to explain the universe. But as soon as the scientific discipline as mathematics, physics were developed, the astronomy were using these resources to explain the universe. So let's gonna start with the universe from the ancient Greek to the current time. So starting with the ancient Greek, first I want to highlight that in the 5th century before Christ, the humans already knew that the Earth was an sphere. Empedocles and Anaxagoras offered different arguments, very strong arguments, to explain that the Earth was round, was a sphere. And this fact was explained through the lunar eclipse. When there is a lunar eclipse, the shadow that the Earth produces is round. So that's allowed to explain that the Earth was round. So many people think that in the ancient Greek thought that there was flat, but this is a misconception. This is not true. From the 5th century before Christ, they already knew that the Earth was an sphere. Aristarchus de Samos, in the 3rd century before Christ, also found out the way to measure the size of the Earth based on the information available for the lunar eclipse. But what happened when there is not a lunar eclipse? It's difficult to explain that the Earth is a sphere. No, there is a way to explain that the Earth was a sphere without using a lunar eclipse. So please check the video I posted in the virtual campus, and this video explains how Eratosthenes found out the Earth was not a flat, and also Eratosthenes found out the circumference of the Earth. In other words, Eratosthenes found out the size of the Earth. So also in the virtual campus there is a little task to be answered for those students who are following the regular attending class assessment. So in the very important model of the astronomy were the geocentric models. These geocentric models were proposed by Aristotle and Ptolemy. First, Aristotle said that the Earth was in the middle of the universe, and there were some planets. In that moment they knew the Moon, Venus, Sun and Mars that moved around the Earth. The stars were fixed in a plane outside of the whole universe, and they were fixed. Also, Aristotle said that there was no empty gaps in the matter. Every matter was like a fixed with 4 elements: earth, air, fire, and water. And there were no empty gaps for Aristotle's elements and cosmology. But this model had a little problem, is that there was wandering planets, planets that their movement were not possible to be explained through Aristotelian model. So to give an explanation from these wandering stars, Ptolemy include a new concept, epicycles. That epicycles are the movement, like the cycle movement that some planets did in order to explain the wandering stars. So there is this is the Earth, and from the Earth there are some planets that in their movement seems to make this wander movement. So Aristotle's model cannot explain this movement, but with the Ptolemy epicycles, this circular movement of the stars, this wandering movement could be explained. After Aristotle and Ptolemy, there was an astronomical innovations based on the discovery of different instruments that allow to observe the universe in a better, proper way. We have different different researchers, so different astronomics that give a lot of information to the cosmos. For instance, the Islamic world between the 8th to the 15th century provide a very wealth of sophisticated astronomical work. Also, in the in the 1543, Copernicus established that the Earth was not in the center of the universe, but the Sun. In this model, all the planets orbit around the Sun, the Moon orbits around the Earth, and again the stars are placed in a fixed plane outside of the universe. So this is Copernicus, like innovations, in 1543. And also a little bit later than Copernicus, like Tycho Brahe, also established his own model of the universe. Again, the Sun is in the center of the universe. All the planets orbits around the Sun, but the Sun orbits around the Earth. Why, like Tycho Brahe introduced this concept? Because with this concept, Tycho Brahe could explain the movement of Mars. Remember that Ptolemy introduced the epicycles to describe this movement, but Brahe, with this new model, could explain the path of Mars without using any epicycles or other instruments. But the important thing of Brahe's model is that these observations and these theories were further used for another important astronomer, Kepler. Kepler quest to bring together geometry and physics to give a new explanation from the planetary orbits. In a very relevant book, Astronomy Nova, Kepler presented extensive research on the orbits of Mars. So here is what I said before. Now astronomy is getting closer to other scientific disciplines like physics and math, and through these math instruments, Kepler could explain the movement of Mars. And this is also important, the Tycho Brahe observation, because were used by Kepler. So what we must know about Kepler? The biggest thing that Kepler provided was he was able to mathematically describe the movement of the planets. There is like a 3 law of the planetary motions, and they are stated as follows. The first law said that all planets move around the Sun in elliptical orbits. They are not making like a circumference, they are making elliptical orbits, having the Sun in the foci of the orbits. So all the planets without exceptions, move around the Sun, and making these elliptical orbits. The second law of law of Kepler's was that a radius vector joining any planet to the Sun sweep out equal areas in equal length of time. So what does it mean? It means like in one of the planet making these orbits around the Sun, where the planet is closer to the Sun, move faster. So in this section, this planet move faster than when the planet is far away from the Sun. In this moment, the planet moves slower. So as closer to the Sun in the orbits, the planet moves faster. When it's far away, the planet moves slower. This is the meaning of the second law. The third law of Kepler's law said that the square of the sidereal periods of revolution of the planets are directly proportional to the cubes of the mean distance from the Sun. So what does it mean? When we have two planets, when one planet is closer to the Sun, it takes less time to complete one orbit. What does it mean? That in this planet, the year is shorter. On the other hand, when we have a planet very far away from the Sun, it takes more time to complete a whole orbit around the Sun. In this faraway planet, the year is longer. So the third law said closer planet to the Sun, years are shorter than planets which are very far away from the Sun. Another important astronomy was Galileo and his finding of the telescope. Galileo is important because he invented the telescope, who allows to determine that the moon was not a perfect sphere. Also, he described that the Sun has is like a spot, and also is moving, is rotating, and also with the telescope of Galileo allows to observe the Jupiter's moon. Galileo observed that the Jupiter has its own moon. But what we need, another important milestone in the astronomy, was the work of the Isaac Newton. Isaac Newton astronomy. What Isaac Newton made was to anchor the astronomy to the mathematical laws. Again, like now, the astronomy was perfectly described with mathematics. So Isaac Newton published a book in 1687, Mathematical Principle of Natural Philosophy, which was a revolution in the physics, in the astronomy, and in science. I just want to highlight the Newton's law of universal gravitation, which stated that every particle in the universe attracts every other particle with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. This, I'm sure like everybody knows this statement, but was authentically a revolution. And the most important thing that Newton did was that he offered a very precise mathematical models to explain the universe. So what is the cosmos today? So what is happening now with astronomy? Important milestones also are the work of Edwin Hubble. Until before Hubble, we only knew about cosmos, that was our solar system and the visible star of the Milky Way. But thanks to Hubble's finding, we know that the universe is more than the Milky Way. Hubble described the Andromeda galaxy, and also Hubble determined that the galaxies are in expansion, are moving are moving away from each other. So this is a very important thing, because if galaxies are moving away from each other, it means in some moment these galaxies were sticking each other. So this is the beginning of the Big Bang theory. Another important thing from today's Albert Einstein's work, the theory of the relativity. Albert Einstein joined energy and mass with the famous equations that space and time are not absolute. Matter is energy concentrating according to a factor equal to the square of the speed of the light. This universally known equation. And also, like another revolution since today's cosmos astronomy is the Hubble telescope. We launch a telescope into a low Earth orbit, and having a telescope outside of the Earth allows us to see further components of the universe, and also was easy to observe that the galaxies are moving apart. And again, if they are moving apart, it's because it was close together initially and there was an explosion. That was the beginning of the Big Bang theory. I want to finish this like a very brief history of the universe with the cosmic microwave background. This is a very recent discovery. So the Big Bang theory predicts that the early universe was a very hot place. We will see this Big Bang theory in the next part of the Unit 1. So it was a very hot place, and that is a span. We said like galaxies are moving apart each other. The gas within the galaxy cooled down. Thus, the universe will be filled with radiation that is literally the remnant heat left over from the Big Bang, called the cosmic microwave background, or CMB. So, thanks to the instruments we developed in the last years, we could take a picture, sign like a picture, of the cosmic microwave background. With this information, we can demonstrate that there was an explosion. So, and these discoveries support the theory of the Big Bang theory.